Okay, so I'm now going to begin with the prediction module. So prediction is a module that allows you to estimate the failure rate of electronic and non-electronic components based on one of a variety of different prediction standards that you can license within the software. If I show you the drop-down box here, you can see the majority of the standards that are available. Each of those standards will be licensed individually. You can see the ones that are available, but you can also get a license for for 217 Plus as well. So that's the one that's missing from that list, but 217 Plus is also available. So the prediction module works in a very simple way. It allows you to build a hierarchy of blocks that represent your system, subsystems, and components, where the component failure rates are estimated using the standard that you've chosen. So I might, for example, start with IEC 62380, fairly commonly used standard. Now I can start building a block diagram or a block hierarchy that represents my system. I can add a system block from the Add menu, or I can do it from the toolbar. So I'll do it from the toolbar, and I might say that this is my subsystem. I'll just call that subsystem. And then below that, I can add more blocks, or I can add component blocks. Naturally, the component blocks represent components in my system. So I can add a component, and I can choose the type of component that I want to estimate the failure rate for. The list of components that you get will depend on the standard that you've selected. So here, for example, because I've chosen IEC 62380, the components that are covered by that standard are the ones that are shown here. And then if I say select a capacitor, for example, and I go to the parameters tab, I can enter the parameters that are relevant for working out the failure rate of a capacitor in the relevant standard. The blue parameters are parameters that are associated specifically with the component itself, so like the component type and the maximum current. The black parameters are parameters that are associated with the operating environment, like ambient temperature and the current that will actually be placed through the component. I can enter these parameters, and when I click OK, the program will straight away automatically work out the subsystem component failure rate, just using the equations from the standard for the selected component type. I can add another component. Maybe it's something different. Maybe it's a resistor this time. For a resistor, we get a slightly different set of parameters. We fill those in, click OK, and again the program works out the failure rate based on the methodology given by that standard. So it really is as simple as that. You can build up as large a hierarchy as you want, populate that with blocks, and the program will work out the system failure rate at the end based on the various components. Now you can also use the prediction module to perform a deratings analysis. The deratings analysis basically allows you to determine which of the components in your system are being overstressed, which components have too high a voltage placed across them, for example. To do that, I would first need to create a derating definition. So I create a derating definition. I'm going to create one for a resistor. This is just showing the deratings definition for the standard that I'm working to. I can only do that for a resistor in this case. I'll do it for all resistor types. I'll do power stress only, and I can tell the program in some cases whether or not there is a temperature dependence. In this case, I can't do that. That's not supported by this standard. So I just enter a derating factor. The derating factor is the ratio between the operating power and the rated power. So the derating factor is just saying I don't want the rated power to go over 100%, the operating power to go over 100% of the rated power. So I click OK, and that creates the ranking, the derating definition. I can go to project options then. On the general tab, I will turn on the derating analysis. Click OK. So let's open up the resistor. So at the moment, the operating power is 1 and the rated power is 1, which means that we've got a factor of 1, which means we're not exceeding what the derating definition requirement. But if I reduce the rated power to 0.8, what I see now is that that block has gone red, because now the operating power has exceeded the rated power, which is not allowed by the derating factor I've selected. So I can use that to see anywhere in my system where I've got components that are overstressed. And I can see that in the derating menu as well. If I click overstressed components, I'll get a list of all the components in my system that are overstressed, and I can click on them, edit them, and check to make sure those parameters are correct. So that's a little bit about how you can set up a prediction hierarchy. It's actually a very simple process. This will also work with libraries in the same way as we saw for fault tree earlier on. We can attach a library project and drag and drop information from one to the other. You can also license parts libraries as well. So there are 3 parts libraries available: electronic parts, IAEA, and NPRD. Electronic parts contains about 100,000 commercially available electronic parts. Parameters have been taken directly from the manufacturer's datasheets. Now, this library does not contain failure rate information. That information will, of course, come from the prediction standard, because if I choose a capacitor, for example, what the program will do is work out the failure rate of that capacitor based on the parameters for the capacitor I've selected. So I can drag and drop that into the hierarchy. It creates the capacitor, and the program automatically works out the failure rate based on its parameters. So that's one of the parts libraries that's available. The other 2 are the IAEA and NPRD parts libraries. Now, both of these libraries are for non-electronic parts. Primarily, they are mechanical and electrical parts, and these libraries do contain failure rate information. For NPRD, for example, if I look at, say, an actuator, just choose one at random. So that's just loading. So there are the various actuators, and here it does contain a failure rate that is based on failures that have been observed in the field, and then written into the NPRD failure library. So I can drag and drop that. And what this will do, instead of creating a specific component type, because of course there's no such thing as an actuator in IEC 62380, what it will do is create what we call an external part. The external part, the program does not calculate the failure rate. Instead, the failure rate is written directly into the parameter, and you can see that's been done here. And the IAEA library would work much the same way. So those three libraries, of those three, only the electronic parts library can only really be used effectively with the prediction module. As I mentioned, there are no failure rates in electronic parts library. They are calculated in the prediction standard. So you couldn't really use this with, say, fault tree or RBD, for example, because there's no failure rate data for them to use. IAEA and NPRD, on the other hand, they can be used with the likes of fault tree as well. You can drag and drop data from the grid into your project and create failure models based on these failure rates. The user parts library is just an extra feature that allows you to build a library like these libraries here, but import them from, say, CSV. So here, for example, is a little bit of imported data in a user parts library. So that's an overview of the prediction module. Again, I'll save questions until the end, but the prediction module is relatively simple. You're basically building a block hierarchy, populating that with components, and then the component failure rates, and from that the system failure rates are calculated using the methodology set out in the selected standard. So from there, we can go to FAMICA. Now you can transfer data directly from one module to another. I'll show you how to do that in a little while, but for the moment we'll look at each individual module and then we'll look at how we can move data between them. FAMICA works in a similar way to prediction in that it allows you to build a block hierarchy. Here though we're doing failure mode, effect and criticality analysis, FAMICA, or we can do FAMIA, failure mode and effect analysis, and we can do FAMIDA, failure mode, effect and diagnostic analysis. You can do any of those. It's up to you which one you need to work to. So in the project options, on the general, you can choose the FAMICA or FAMIA standard that you're working to. You can see the most common options there. I'm going to stick with MIL 1629 for the moment, then maybe show one or two of the others a little later. So if I click OK, and I'll start by, say, double-clicking this block. I'll say that that is my system. And then underneath that, I can add a block. I'll call that maybe a subsystem. And then beneath that, maybe I'll add one more. I'll call that component. Just like the prediction module, I can add as many blocks as I want to as many different levels. I'm not limited in that. But at this stage, what I would do is add failure modes. Failure modes can be added at any level of the hierarchy, but typically you would start at the bottom and work your way up. So I'll add a failure mode to the component. So maybe I'll call that short. And I can say what percentage of component failures come from this failure mode. So maybe it's 50%. Now I'll add another one. That will also be 50%, and maybe I'll say that fails open or something like that. And for the component itself, the component block, if I double click on that, I can give it a failure rate. As I mentioned, this can be transferred directly from prediction as well. So you may not have to enter the failure rate manually, but I will do that in this case. So if this failure rate, 10 to the minus 5, 50% is coming from each one of these failure modes. Now there's quite a lot you can do with a failure mode. For example, you can set up IEC 61508 parameters. Tell the program what percentage of failures are dangerous, what the diagnostic coverages are. This is useful if you are dealing with, say, a FMIDA under IEC 61508. You'll see also that there are ISO 26262 tab as well. So you can say whether or not a failure is safety related, what the percentage of safe failures is, potential to violate safety goal, and so on. These are the parameters that we need to work out those metrics that are set out in ISO 26262. Again, I'll come back to those a little bit later. For now, we'll keep it quite simple. We'll just say short causes 50% of failures of a component, and now we'll define what the effects of that failure are. So I'll add an effect. I'll just, again, keep it simple. I'll call it effect 1 and click OK. And this will add an effect at the next level of the system. So you can see there's subsystem. I'm going to add that at the subsystem level. I can, if I wish, have that appear at a higher level of the hierarchy. For example, effect 1 might be an effect that appears at the system level. Maybe the short immediately causes a system failure without any intermediate effects. But in this case, I'm going to stick with the next level effect. And I can have multiple effects if I wish. I can add another one. Maybe it also causes effect 2. If I click OK, there I can see the component short failure has 2 effects, and they appear as failure modes at the next level. Component 2, the open failure mode, I can add an effect for that too. And I can add a new effect, or I might say, well, actually, the open failure also causes effect 2 as well. So it could be not only one failure mode causing multiple effects, but maybe multiple failure modes resulting in a single effect. So you can do it both ways. So I click OK, and now you can see both of those failure modes result in the same effect. I can see that at the next level too, where effect 2 has 2 different contributors. And I simply continue that way up the hierarchy until I get to the top level where I'm defining my end effects. So I'll just have one called end 1. And I'll add one for the other effect called end 2. So you're basically creating a chain from the bottom of the hierarchy where the component failure modes are, up to the top of the hierarchy where the end effects are. So this kind of gives us a familiar. We've got our failure modes and we've got our effects. What we don't have yet is the criticality for the FMICA. Criticality, we need the severity rankings. We need to rank each failure end effect by its severity. I can do that here using the severity ranking library. So I'll add an effect, a ranking, and then we'll enter a description. So I might call that, say, 1. That might be major, and that has a weight of 50. Weight is like what we saw for consequences in the event tree. It's just a dimensionless value that indicates how serious the problem is. Add another one, 2, moderate, and that might have a weight of 20. Then we'll just have like 1, 2, 3, minor, and then that will have a weight of maybe 5, let's say. So I can have as many rankings as I want. And then for the end effects, I can say this end effect has a severity that's maybe a moderate. maybe this one is major. And you can see those rankings are added. So now I can analyze this Formica. I click to perform the analysis, and we can see straight away there are some results in the hierarchy. The program, for one thing, will use the failure rates of the various component blocks to work out the failure rates of the blocks higher up the hierarchy just by summing them together. It will also work out criticality. That's those CR1, CR2, CR3, which isn't included here because I've not used the ranking 3. Criticality is the product of the weight of a consequence and the associated failure rate. So here, this is the criticality is actually just the failure rate that's contributing to each severity ranking. So severity ranking 1, the major severity, has a failure rate of 10 to the minus 5, whereas the moderate has 5 times 10 to the minus 6. Then the risk is the sum of the criticalities multiplied by the relevant weight. So the criticality weight here, that would make that 5 times 10 to the minus 4, and this would be 20, so that would be 1 times 10 to the minus 4, and so what we'd end up with is basically 6 times 10 to the minus 4. It's just the criticality multiplied by the relevant weight summed together to give the risk. We can see that in the results summary as well. Now you can see here there are stats also for ISO 26262 and IEC 61508. I'll show a quick example of ISO 26262 maybe. So I'll just see if I can find a good example here. Open that. So here I can run an analysis. I can pull up the results summary and I can see things like single point fault metric. I can see the latent fault metric, MPFD, MPFP, and so on. So the various different metrics and values for the failure rates, and basically based on ISO 26262. Now, we can also provide a report that will produce a FMEDA as set out in ISO 26262 as well. So if I go and find that report, which I think, look a bit further down. I think that's the wrong version of the report. I need the 64-bit version, which is that one. There we go. So you can see this actually reproduces the FMEDA from the back of the standard itself, along with the metrics and so on. So you should be able to reproduce the FMEDA methodology in the Formica module of Reliability Workbench. So very quickly, I will close that and I will pull up another prediction module, prediction example rather. What I will do is show you how you can transfer data from one module to the other. So there are lots of different conversion options in Reliability Workbench. For example, if you go to Special Functions and go to Convert, you can go from prediction to Formica, RBD, fault tree. You can also go from Formica to fault tree and RBD, and from RBD to fault tree. The only thing really you can't do is go from fault tree back to reliability block diagram, because the RBDs are very free form, and from a developmental point of view, that conversion will be very, very difficult to do. But all the other conversions you can perform. What I'm going to do is I'm going to go to the project options, and under data links, tell the program to assign a data link on intermodule copy. This means that when I convert from prediction to Formica, I will link the failure rates in Formica to those in prediction. So if I modify the prediction failure rates, I can easily pass those changed rates over to the Formica module. So I'll now go to special function, convert prediction to Formica. And there you can see the program has converted that information across. You can see there the failure rates that are coming from prediction. You'll notice also that there are failure rates there as well. Sorry, not failure rates, that there are failure modes there as well. These are coming from the apportionment library. What I've done is created a library under the apportionments library, which is this button here. I've created a library of components and their associated failure models. And the program is able to recognize part descriptions and part numbers in the prediction module. So when I pass them across, the program will see, okay, well, this alphanumeric display has the same part number or the same description as this alphanumeric display in the apportionment library. So what I'll do is I will give it the same failure modes. If you look here, that's what it's done. So you can automatically attach the relevant failure modes to the components on transfer to prediction to Formica. So one last module to look at today, and that is reliability block diagrams. And we can actually be relatively quick with this because a lot of it is in common with fault tree. So reliability block diagram allows you to build the logic of your system not as a tree, but as a system of blocks that are connected together in series or in parallel, and basically model your system that way. So instead of adding a top gate, we would instead add a new system. So I can add a system from the add menu, or I can do it from the toolbar. So I can add a new system, and that appears in the tree control. And again, maybe I can change the name of that just by double clicking on it and editing its ID. And then I can start building the block diagram itself. So where a fault tree is made of gates and events, an RBD is made of blocks, nodes, and connections. The blocks represent systems, subsystems, components, failure modes, or any other events that could occur in your system. So I can click to add a block, or I can add a block from the toolbar. Then I can left click in the diagram to add blocks where I want them to be. Now I can right click and clear add mode, and that takes me back to the regular cursor. So if we look here, I might want to connect these two blocks in parallel, which means I need a common point at which to connect those blocks together. And that would represent maybe block 1 and block 2 being two components that are redundant. They're in parallel. So I can add nodes. The nodes are what allow me to connect blocks to one another. So I'll add a node here, I'll add a node here. I can move those around as well by clicking on them and dragging them where I want them to be. And now it's just a matter of connecting those blocks together. So I click Add Connection, which is this button, or this button. They're just different shape connections. It doesn't affect the analysis. It's just which one you prefer aesthetically. I'll choose horizontal and vertical. I click on the node where I want the connection to begin, then click on the block where I want it to finish. I can just do that, click on the block, click on the node, click on the node, click on the block, and that will connect all those objects together. And now I can start to build up the logic of my system. Now, I might want to break my system into subsystems, a little bit like the pages that we saw in fault tree. If I want to define a block as being a subsystem with its own internal structure, what I can do is I can select that block, maybe we'll choose block 3, click on the page down button here, and that now takes me inside block 3. And I can add more RBD structure down here. I'll connect all of those together. I don't need nodes here because these are just in series. So there's no parallel arrangement, so no nodes are required. So now block 3 appears as a subsystem block underneath system. If I go back up to the system level, I can see block 3 has that icon next to it telling me it's a subsystem with its own substructure underneath. After that, I can define failure data, and I would do that in exactly the same way as I would for a fault tree. I can use local failure models for the blocks, like I did with the events in the fault tree, or I can define generic failure models. So I might use a simple rate model, and I'll just use that for all of the blocks. I can just drag and drop that onto the blocks that I want to use it. Oops. The program can also accommodate common cause failures. It can link to Markov and to Weibull the same way as we saw with the fault tree. In the project options, it's similar to the fault tree, maybe a little bit simpler. We have the cutoffs as before. In the custom options, I'm just going to tell the program, expand the modularized sets. Again, you can see this is much more simple than the fault tree. Calculation options are pretty much the same. So I might set a lifetime of maybe, I don't know, let's say 1,000 hours, for example. And I'll turn on the time-dependent analysis to get those plots as we saw earlier. So I analyze the RBD, look at the results. I can see results from my system block, unavailability, failure frequency, and so on. The importance of the different component blocks to failures of a system, and the cut sets, the sets of blocks which if they fail together will cause a failure of my system. I can get that information for subsystem blocks as well. So block 3, for example, I can see that under the subsystem option, and I can get results for that too. And of course, we also have access to plots that show us similar things to what we saw with the fault trees. And we can see importance as well. So all of those controls work the same way. And like in fault tree, you have access to the grid, which can show you blocks, or it can show you failure models, and so on. You have access to the libraries option if you want to pull data from the library project. And you have access to the parts libraries too. So let's show how these modules work together. I'll open a Formica example where I could go, say, to special functions and convert from Formica to RBD. But I can use project options to structure that to some extent. Under the Data Links tab of the project options, I can ask the program maybe to build the RBD or the fault tree from the Formica in a different way. Do I want to go all the way down to the root failure mode level or not, for example? So I might say, yes, I do. So I would then convert Formica to RBD. And there you can see the program's created an RBD based on my Formica. And I can also, of course, convert from RBD to fault tree or from Formica to fault tree. All of these options are available. So that is an overview of prediction, Formica, and RBD. So I appreciate that's quite a high level overview because we have relatively limited time to cover the 3 modules. So I'll